moving electric charges produce magnetic fields. For example, an electric current deflects a magnetic compass needle placed in its vicinity. The phenomenon in which electric current is generated by varying magnetic field is appropriately called electromagnetic induction. The experiments of Faraday and Henry. The discovery and understanding of electromagnetic induction are based on a long series of experiments carried out by Faraday and Henry. The experiments of Faraday and Henry. In this animation, a coil C1 is connected to galvanometer G. When the north pole of a bar magnet is pushed towards the coil, the pointer in the galvanometer deflects, indicating the presence of electric current in the coil. The deflection lasts as long as the bar magnet is in the motion. The galvanometer does not show any deflection when the magnet is held stationary. When the south pole of the magnet is moved towards or away from the coil, the deflection in the galvanometer are opposite to that observed with north pole of the similar movements. When the bar magnet is held fixed and the coil C1 is moved towards or away from the magnet, the same effects are observed. It shows that the relative motion between the magnet and the coil that is responsible for generation of electric current in the coil. Magnetic flux. Faraday's great insight lay in discovering a simple mathematical relation to explain the series of experiments he carried out on electromagnetic induction. However, before we state and appreciate his laws, we must get familiar with the notion of magnetic flux psi b. Magnetic flux is a scalar quantity. Faraday's law of induction. From the experimental observations, Faraday arrived at a conclusion that an EMF is induced in a coil when magnetic flux through the coil changes with time. The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. Lenz's law and conservation of energy. The polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. Motional electromotive force. Let us consider a straight conductor moving in a uniform and time-independent magnetic field. A rectangular conductor PQRS in which the conductor PQ is free to move. The rod PQ is moved towards the left with a constant velocity v. Assume that there is no loss of energy due to friction. PQRS forms a closed circuit enclosing an area that changes as PQ moves. It is placed in a uniform magnetic field B, which is perpendicular to the plane of this system. If the length RQ is equal to x and Rs is equal to L, the magnetic flux psi b enclosed by the loop PQRS will be psi b is equal to BLX. Energy consideration, a quantitative study. Let R be the resistance of movable arm PQ of the rectangular conductor. We assume that the remaining arms QR, RS, and SP have negligible resistances compared to R. Thus, the overall resistance of the rectangular loop is R, and this does not change as PQ is moved. Eddy currents. So far, we have studied the electric currents induced in well-defined paths in conductors like circular loops. Even when bulk pieces of conductors are subjected to changing magnetic flux, induced currents are produced in them. However, their flow patterns resemble swirling eddies in water. These currents are called eddy currents. Eddy currents. Consider the apparatus. A copper plate is allowed to swing like a simple pendulum between the pole pieces of a strong magnet. It is found that the motion is damped, and in a little while the plates come to a halt in the magnetic field. Magnetic flux associated with the plate keeps on changing as the plate moves and out of the region between magnetic poles. The flux change includes the eddy current in the plate. Direction of the eddy currents are opposite when the plate swings into the region between the pole and when it swings out of the region. Eddy currents are used to some applications like magnetic braking in trains, electromagnetic damping, induction furnace, electric power meters. Inductance. An electric current can be induced in a coil by flux change produced by another coil in its vicinity or flux change produced by the same coil. Mutual inductance. Varying current in a coil can be induced EMF in a neighboring coil. The magnitude of the induced EMF depends upon the rate of change of current and mutual inductance of the two coils. Self-inductance. The flux in one solenoid due to the current in the other. It is also possible that EMF is induced in a single isolated coil due to change of flux through the coil by means of varying the current through the same coil. This phenomenon is called self-induction. AC generator. The phenomenon of electromagnetic induction has been technologically exploited in many ways. An exceptionally important application is the generation of alternating currents AC. The modern AC generator with a typical output capacity of 100 megawatt is a AC generator.
Suppose that the generator coil ABCD is initially in the horizontal position. Again, suppose that the coil ABCD is being rotated in the anti-clockwise direction between the poles north and south of a horseshoe type magnet by rotating its shaft. As the coil rotates in the anticlockwise direction, the side AB of the coil moves down, cutting the magnetic field lines near the north pole of the magnet, and side CD moves up, cutting the magnetic field lines near the south pole of the magnet. On applying Fleming's right-hand rule to the sides AB and CD of the coil, we find that the current are in the directions B to A and D to C. We get an effective induced current in the direction BA DC. Thus, in the first half revolution of coil, the current in the external circuit flows from brush B1 to B2. After half revolution, the sides AB and CD of the coil will interchange their positions. The side AB will come on the right hand side and side CD will come on the left side. So, after half a revolution, side AB starts moving up and side CD starts moving down. The direction of induced current in each side of the coil is reversed after half a revolution, giving rise to the net induced current in the direction CDAB. The current in the external circuit now flows from brush B2 to B1